Hey everyone, in this video I'll be going over Learning Target 23, which is about evaluating definite integrals using the fundamental theorem of calculus. So in this first part, part A, we need to use FTC, the fundamental theorem of calculus, to simplify this expression. So I'm seeing a derivative and an integral, and typically that just means that cancels out. But because we have the actual function itself in terms of t, and the bounds are in terms of x, we need to replace that, plug it in, and also we're taking the derivative, so we need to use the chain rule. So I'm actually not going to be taking the integral or the antiderivative of that function because the derivative and the integral cancel out. But what we're going to do, we have to do, is replace that t with x squared plus 1. Sorry, plus 1. This pretty much goes into there. Still plus 7. But then now, as I mentioned, we have to use the chain rule and take the derivative of that upper bound, x squared plus 1. The derivative of that is 2x. So there we go. That's our answer. Didn't actually have to take the antiderivative, just recognizing the fundamental theorem of calculus. Now in part B, we have a few definite integrals we need to solve. So now we take our antiderivatives. So really quickly, I'm going to rewrite this in a little bit easier form to understand. I'm going to use 4x to the 1/2 dx. That x to the 1/2, it just helps me do the power rule a little bit easier. So I'm going to keep that 4 there, and I'll have x, and the exponent will be 1/2 plus 1, so 3/2. And then now we divide by that exponent, which is the same as multiplying by its reciprocal, 2/3, and the bounds from 0 to 4. Simplifying that a little bit more, we'll have 8/3 x to the 3/2 power, bounds from 0 to 4. So I'm just going to take that 8/3 out in front. It's a constant coefficient. We'll have 4 to the 3/2 minus 0 to the 3/2. Those are our bounds. 0 to 3/2 is just 0. So I will just have 8/3 times that 4 to the 3/2 power. This is not too terrible to solve. 8/3 times 4 to the 3/2. That 4 to the 3/2 becomes 2 to the 3rd power, because that 1/2 power is a square root. The square root of 4 is 2. Same as 8/3 times 8, which just leaves us with 64/3. And we don't need a plus c here because this is a definite integral. I think on the last video with antiderivatives, I wrote a big plus c at the top, so I'm going to write plus c, and we're going to x that out. We don't want plus c's with definite integrals. The reason we don't need plus c's with definite integrals is I don't really have a lot of room for it, but if I were to keep a plus c, I'd have like a 4 to the 3/2 plus c minus 0 to the 3/2 plus c, where that c gets subtracted away. So it just cancels itself out. So it's not really there anymore. Okay, now number 2. Got a trig integral. Not too bad. Antiderivative of sine is going to be cosine. And our bounds are from pi over 6 to pi. So I'm going to take that negative out in front again. It's a constant coefficient. I'll have cosine of pi minus cosine of pi over 6. We'll use that top bound first and subtract away the bottom bound plugged in. Cosine of pi, using our unit circle, is -1. Cosine of pi over 6 is square root of 3/2, but we're subtracting it. We can distribute that -1 out in front, and we get 1 plus square root of 3 over 2. You could simplify that a little bit more. I'm just going to leave it like that. Finally, one last question. This also looks like power rule to me. Well, it looks like it could be put in a good form for power rule, so I'm going to do that. 1 over x squared is the same as x to the -2 power dx. Then taking the antiderivative, I'm going to add 1 in that exponent, so I'll have x to the -1. I need to divide by this -1, which just means I'll have a negative out in front. And that's from 3 to 6. So I'll have negative. I'll plug in 6. 6 to the -1 power is just 1 over 6. Subtracting 3 to the -1 power is 1 over 3. 1/6 minus a third is -1/6, but I have this negative out in front. So the final answer is 1/6. Alrighty, going back to part A, a little summary. Fundamental theorem of calculus says if we take a derivative of an integral, those effectively cancel out, but we need to make sure we change the variable to whatever's in the bounds in that derivative. That's x, but in the function we have t. So wherever there's a t, we now plug in an x squared plus 1. We also got to make sure we multiply by the derivative of the upper bound because of the chain rule. When we do definite integrals, we don't include a plus c because they would just be subtracted out, canceled away. In this first question, I see a square root. I'm going to rewrite it in terms of exponents, so that way we can do the power rule pretty easily. And then I plug in the upper bound and subtract the lower bound. In this case, the lower bound is 0, so we don't really have to do it. Sometimes you have to do it, but in this case, because it's just something times x, 0 to whatever power is just 0. So I think it's good practice to generally do it like this. You don't always have to, but I think it's good practice. Part number 2 was pretty much the same deal, just with trig. Make sure you memorize those trig antiderivatives. And then also in part 3, recognizing we can do a power rule for this too, plugging in your bounds and getting an answer. Not too bad.